so I think it's time to start. So welcome again to this week's installment of the Topics in Gravity course. I hope you're all doing well. I wanted to go a little bit again just over the conceptual aspects of what we established last time. Well, I said last time that I would give you a list of diagrams and so on, but I decided actually against it because I think it is actually better really if you go through this paper by Jeroen Bohr et al. So that also has Donahue in the list of authors, which actually does a very good job, I think, in drawing the diagrams and just applying the Feynman rules and giving you the answers. And the only difference to what we did last time is that you really have the exact coefficients with every diagram. And I think that would have not been a good use of our time, because I would like to move on, in fact, already today to the subject of physics in anti-de Sitter space. Of course, I'll motivate it a bit. So let me just go, therefore, over the, as I said, conceptual aspects. So in some sense, sort of really as a proof of principle of many of the things that we have learned, basically, we discovered that we could use just flat space quantum gravity in a low energy theory, as a low energy theory, to make some unique quantum predictions about how gravity behaves. So the main idea is that, well, because we are only interested in, let's say, low energy physics, we can use the idea of effective field theory, and we can make GR work in that way as an effective field theory. And in particular, within that effective field theory, we study a process or processes of the kind where we have some massive objects, which, for example, are conveniently described by, say, a massive field or just some massive source that you couple to. And we look at how these objects behave if you let them interact via our spin 2 quanta. So what I've written here schematically is that there is any kind of exchange process that involves gravitons between them. So obviously the simplest one that you could imagine is just a tree level exchange. And so, of course, there's a lot of work that goes into actually doing these calculations, and the complications mainly come from the fact that spin 2 objects are kind of messier because they have more indices, and so you need to work a little bit harder to deal with essentially the polarization structure of the theory. And secondly, of course, we're dealing with a gauge theory, so you also have to deal with gauge fixing and so on. But in the end, it can be done in actually using standard methods that you would also use in like other more familiar gauge theories like electromagnetism. And the result that we get from basically we interpret this these types of amplitudes as being more or less the Fourier transform of the potential, as we said last time. And so then from this amplitude in momentum space, you can actually deduce excuse me, you can deduce a potential in X space. And that potential takes the form that I've written down here. So you have a piece, so I've written it basically where I multiply everything by the Newton potential. So G is the Newton constant, and then of course the product of the two masses divided by R. And then the leading term, which is just that Newton potential, is what you get from just having tree level graviton exchange here. And then by including the one loop terms from Einstein-Hilbert, as well as curvature squared interactions that contribute at the same order, we can actually extract some corrections to this, which, well, one can physically distinguish into, there is what we call the relativistic correction, and then, so it doesn't contain H bar notably, and then there is the bit that we really find the most interesting one, which is the long range quantum correction, which is of this form. So there's some coefficient 41 over 10 pi times GH bar over R squared. So overall, it's a term that goes like GH bar divided by R cubed. And in particular, it's a quantum correction proportional to H bar. So overall, let me just make the comment that both of these terms, both of these terms here, both of these terms came from the non-analytic parts of the one loop amplitude. And well, I'll go over why in a second. But the one, as I said, that I would most like to focus on is this, this thing that's a quantum correction. So for this, well, I suppose I'm explaining it here, right? So if you have something that goes like a non-analytic term, there are two kinds of non-analytic terms that you encounter. There are non-analytic terms of the form log q squared, and there are ones that go over, say, log absolute value of q, the momentum. And the point is, if you Fourier transform these, so you go from Q space to R space, then what you find is a term that goes like either like 1 over R cubed or 1 over R squared. It's just that I seem to have written the wrong powers here, right? Because we say this thing here, this one, it goes like 1 over R squared, and this one goes like 1 over R cubed. So I think I got the powers wrong here. Let me just correct that. Apologies. So this, so we said this was going to be 1 over R squared, and this was going to be 1 over R cubed. Okay, and so the main point is, really the main point is that all other terms that you get at this level in the EFT expansion will be analytic in momentum, meaning that they will be something like proportional to 1 or some positive power of momentum, some analytic expression in momentum. And you can convince yourself that all of these analytic type contributions in momentum, if you Fourier transform them, they lead to very short range interactions. So delta functions or derivative of delta function type interactions. And so you can qualitatively distinguish them from terms of this kind, which have sort of more long range character, which go like some inverse power of R. And so the magical thing that happened was that all of the contributions that come from non-Einstein-Hilbert type interactions, so interactions that are of the form curvature squared in this case, and whose coefficients we do not know, all of these corrections can be distinguished from the kind of things which we've kept here, because they are super short range. And let's say in the infrared limit, in the low energy limit, we're interested in more like, infrared, so long distance properties. And so these long distance properties here are uniquely a property of the Einstein-Hilbert action. And in particular, it contains a quantum correction. And so there is a unique, fully determined quantum correction that comes only from the structure that we know, namely the Einstein-Hilbert term. Well, it takes this form. And so the important bit is that this gives us what I would call a universal low energy quantum prediction from purely Einstein-Hilbert, just by taking it seriously as a quantum field theory, which we can by working within this effective field theory framework. And so in that sense, it is a theoretical milestone that every functioning theory of quantum gravity has to measure up against, meaning that if you want a theory that works well in the UV, and you want to make some claim that it also approximates our world at low energies, then it better give this kind of correction. So Einstein-Hilbert, of course, the classical limit, but also this kind of correction. And so it's a fairly stringent test. So it's in some sense some kind of low energy theorem that one can use in one's exploration of quantum gravity. Now, that's the only really concrete calculation that I want to go over. There are obviously other calculations that you can do in using gravity as an effective field theory. One very famous one being obviously this famous calculation of Hawking himself, who calculated the radiance of a black hole using essentially GR as an effective field theory. Yes, maybe within ADS, the ADS part, we'll have some time to go over that calculation. Maybe not, but I just wanted to make you aware of this one, because in some sense, it's really a very classical result, which is for some reason less known than the result about black hole radiance. Okay, so let's move on then. So we've said that basically these long-range corrections that we wrote down here are unambiguous quantum predictions of low-energy quantum gravity. But the issue, of course, is in some sense you could say that's an experimental prediction, right? And it is, of course, but then you need to ask yourself, how big are these effects? And the answer is that these effects are absolutely minuscule. They're really, really tiny. So, so let me write, however, these are tiny. Let's say in any normal situation. Okay, so let's say, for example, we take the radius at which we evaluate this correction to be, say, the radius of Earth, just for example, okay? Then what we get, so we have these two different effects, right? So we have the post-Newtonian correction. This is g times the mass of the Earth times r times c squared. This, if you put in the numbers, you get 10 to the minus 6. Okay, but the more interesting bit, so the one, of course, that we focus on in the context of this course is the second one, which is the quantum correction. So this is of the order g h bar over r squared c cubed. Okay, and this is of the order 10 to the minus 88. So absolutely tiny. Okay, so the quantum correction for sort of objects that or processes that happen on the scale of Earth is 10 to the minus 88, the relative effect to what the Newton potential is. So absolutely, absolutely tiny. But what we can ask, of course, is so, relativistic effects, yes, we have a chance of measuring them, and of course we are, but quantum effects, we're not measuring them on Earth, of course, but we can measure them in astrophysically relevant objects, but, or we can hope to measure them in astrophysically relevant objects, I should say. Maybe some of you are more experts than this, but I don't think these post-Newtonian corrections have yet been measured, but that's obviously some kind of target for objects, for experiments like LIGO and so on. But focus on the quantum thing. So let's ask the question, when is this quantum correction, GH bar over R squared C cubed, an order 1 correction? And so, any guesses?
Planck length.
Yes. So if we were on a, measuring gravity on a scale, so I just obviously solve this for R. So R should be C cubed over G H bar square root, okay, which we call the Planck length. So precisely this form is of, is an expansion, if you want, in length scale over the Planck length. So these quantum corrections or quantum gravity corrections become important if we talk at scales of order, the Planck length, or so the Planck mass, and whatever else you might think of associated with Max Planck. So, however, so that again, in retrospect, that's not a big surprise, and also in retrospect, right? One could have just used intuition. One could say, well, what is the first? What is going to be the order of magnitude of the first quantum correction, and one would have said, well, it's going to be, let's say, L over L Planck, or L over L Planck to the right power. The only thing that we've done here is we've actually fixed that coefficient, if you want. So, okay, but also from our perspective, I think it does add a nice further item in our exploration, which is that this naive kind of approach that we have, or maybe it's not that naive, but the approach that we have, let's see, well, let me use the word naive in the sense of, if we just quantize GR, okay, we just pretend that we quantize GR. So that's the meaning of naive. So this naive approach to quantum gravity well, it becomes non-perturbative, meaning that it becomes an expansion in the coupling that's greater than 1. Non-perturbative at, Planck length, let's say. So we're really in trouble. We're leaving definitely the realm of effective field theory once we look at processes at around the Planck scale. So we can make sense of this theory at most up to the Planck scale. And as I was saying a few times, we can of course also choose to have some cutoff which is way below the Planck scale if that's more convenient for us. But what this is telling us that we definitely cannot go beyond those scales. So that's really where we cannot make any sense anymore of this theory. Okay, and so then the question arises, obviously, how do we go beyond this? So there is not a good theory of spin 2 objects at the Planck scale using the approach that we have. So the question is then, how do we construct? So how to construct, let's say, a consistent S matrix of something like a spin 2 massless object. At the Planck scale. So that's the big question. And well, there are a number of answers. The ones that I'm most familiar with, so one I would write here is basically you go to string theory. So instead you construct objects which aren't point particles but are instead strings. And in 10 dimensions, in fact, this does give you a perturbatively well-defined S matrix in the UV. But that's not, at least not in a direct sense, the route that we're taking. So what we're going to do is we're going to use a different idea. We're going to go to this idea of holography. And that's basically the second part of the course, or whatever remains of this course. So this is basically part 2 of topics in gravity. Okay. So, excellent.
Can I ask a question?
Yes, but maybe before you ask that question, though, I will make one more comment, just as an aside. Okay. The point is that it is possible, and in fact, more and more recent evidence mounts that also it is the case, that this effective field theory of gravity, it must break down at the Planck scale, but it may break down at scales which are actually below the Planck scale because of other subtle effects that general relativity contains, but in particular, non-local effects like for example, the horizons, right? Horizons are something that's non-local. And we think that perhaps the presence of horizons also gives contradictions to the predictions of effective field theory, but already at scales far below the Planck scale. Also, if you think about time dependence, okay, to describe the full time dependence of the universe using effective field theory, it is far from obvious that you can do that, and the breakdown isn't necessarily at, say, Planck times, and various other things that are happening, which suggest that other subtle effects can actually get you before you even get to the Planck scale. But that's not that's not the focus of this course. I just wanted to motivate what we're doing next, namely that we look for a UV completion by what we can absolutely with certainty establish, namely that at the Planck scale, using what we've done, we get into trouble. Right, Manus, you had a question.
Yes, thanks. I have two questions.
Oh, yeah.
One is about the factors of C in the equation on the previous slide. Did you put them equal to 1?
Yes, I did. Yes, I
okay.
did.
So, okay. And the other question is whether curvature square terms could actually contribute, you know, at a smaller or at a larger scale than the Planck scale. So why aren't they more important than these quantum corrections?
They can, but I think that they would at the next order in loops. So don't ask me to do this now in my head, but we said that at a given order in the EFT expansion, so any process of the energy over cutoff, so here it would be energy over Planck energy, right? We're at the order E over E Planck squared here. And we've shown that the only contributions that you can get are loop diagrams from Einstein-Hilbert and tree diagrams with the curvature squared interaction. And so there, the only long-range contributions come from Einstein-Hilbert. But if you go to the next order, meaning E over E Planck to the power 4, then you can also get one-loop corrections from the curvature squared interactions, which can give you, you know, long-range type contributions, but they would be suppressed.
That depends on the coefficients of the
no,
squared,
they're suppressed in the scale of the process over the Planck scale, over the cutoff scale. There might be some, yeah.
Okay. Thanks.
Okay, so, all right. So that really is the end of the part on flat space quantum gravity, or low energy quantum gravity if you want. And now, as I said, if you wanted to do things just in flat space for now, then the direction to go would be this direction here, or any other ideas people have about the UV behavior of 4-dimensional, or let's say just flat space gravity. Okay, and there's of course tons that can be said. But what I'm going to do is, so we've had a bit of sort of symmetry-driven approach to this, right? We really started by discussing the symmetry content and basically sort of trying to almost axiomatically build up to where we are now. So what I'm going to do now is I'm going to also have a symmetry-driven approach, but I'm using enhanced kind of symmetries. And this is going to basically lead us to studying physics for now in anti-de Sitter space. So let me start this. So this is now the part that we have on the ADS-CFT correspondence. But of course, please feel free to ask more questions, right? I mean, this is like a big turning point now in this course. So I mean, it's not like it's your last opportunity to ask questions, but maybe you have some right now before we move on. Okay, well then I will move on. So let's see. Well, what I have here, let me just remind you one more time about just what kind of was our philosophical approach here. So in flat space, what we said is we basically start with the idea that we have, we want to really work on the basis of Poincaré invariance, and let's say in 4 dimensions in our case. And so what we had was we had our Lorentz generators, which we summarized as omega mu nu. We also had translations, which were this vector a mu. And there were obviously 6 of those, and there are 4 of those. And this in total gave us the 10 isometries of flat space with signature 1,3. And if you want, you can formalize this and you can say that basically this R 1,3 is a maximally symmetric space. And from just differential geometry, you can say that it has exactly in 4 dimensions, okay? Exactly 10 and not more isometries. So what we have is we have a geometric action of the isometries of our where we have a geometric action of our symmetries, namely Poincaré, as the isometries and all of the isometries of a certain space, namely Minkowski space. So Minkowski space is in some sense the geometrization of Poincaré transformations, which is something that you know, of course. Now, then what we were saying is, well, we basically demanded that we have an S matrix which respects this Poincaré that has satisfies unitarity, causality, and locality constraints, and we build up the theory from there. But what we found is that, okay, this leads us to, let's say, gravity as Einstein EFT, one can call it like that. However, what we found is that it is not well defined in the UV. So this is great at low energies, but problematic in the UV. So in particular, of course, we have shown that it's a non-normalizable theory, and also that the effective field theory treatment becomes non-perturbative at the Planck scale. So in order to cure this, okay, in order to address this, what we need is, in order to cure this, I wanted to say, in order to cure this, we need some radical departure. Some radical departure from our principles, right? Because our principles were already very constraining. So let's say from standard approach. And so the radical departure that we are going to implement is that, one, to say it with a bit of poetic license, gravity isn't really there. So gravity is actually emergent. And two, because we've had some very stringent constraints on emergent gravity, basically it doesn't really work, but on the basis of our symmetry principles. We also need to enhance the symmetry. And what we're going to do is we're going to replace our symmetry principle, namely the Poincaré symmetry, with conformal symmetry. And that will lead us to something like the ADS-CFT correspondence. And I would like to develop this as much as I can, or as much as one can, also using symmetry-based approach. So I guess I can just say this leads us to ADS-CFT, or holographic duality, which is actually a better name for it, but let's be strict right now. ADS-CFT, holographic duality. And I see there's a question, just one sec. Okay, I'm just gonna write this. Holographic duality. Yes, please.
So I mean, but we've changed the space-time in which we are quantizing gravity, right? So there is no way by this principle to quantize gravity in flat space-time.
Well, I have not yet done that. We will actually derive what happens to space-time, but of course you know it, so you're anticipating this result.
You change the symmetry group, that's what I'm asking.
Yes. but I don't want to make the statement that there is no way of quantizing gravity in asymptotically flat four-dimensional space based on asymptotic Poincaré symmetries, because there are many people that claim that they can do it. But I don't know. I mean, I'm not an expert in any of these, so you know, we would be talking about things like loop quantum gravity and so on. But what I can say with certainty, because we've established it, that this effective field theory, so the sort of naive quantization of the naive quantization, no, we can say it stronger, so strike effective field theory. The naive quantization of Einstein-Hilbert just doesn't work, okay? And the symmetry-based approach would lead you to the naive quantization of Einstein-Hilbert. Of course, again, like subtlety, okay, we have also shown that at low energies, at least, still we can make sense of this as a quantum theory, but that's just because of this wonderful structure of effective field theory. That's not a statement about the UV. Okay?
Okay.
Okay, so great. So now we're going to, you know, go back to the beginning where we talked about unitary representations of the Poincaré group. And what we're going to do is we're going to go over the conformal group. So we're going to go over the representation theory of the conformal group. We will do it in a way that evokes maybe what we did on the Poincaré group, but what I would like to do is I would like to work in also a geometric perspective that we didn't emphasize so much, which is why I see there's a question, just one sec, which is why I mentioned this now here, is that basically the space-time that we've worked with is the perfect space-time adapted for Poincaré, because the isometries of the space-time itself are the Poincaré group. So there's a geometrization of our symmetry group. And we're going to work towards and with a similar geometrization of the conformal group. And that, let me just anticipate it, that will lead us to this anti-de Sitter space, but we'll derive that. Okay, was a question, please.
Yeah, sorry, Julian. I would
Yes.
like to ask you,
yeah,
what is the motivation for doing this? In the end, we had a theory which is able to compute whatever order you want, quantum correction to gravity, no?
Yes, but it's not something that allows us to talk about processes at the Planck scale, which is, so it's not, we can't really talk about the UV. And so if you talk about, for example, extremely high curvature objects, so obviously the example that people give is what happens to singularities in black holes, or what happens to cosmological singularities, or, you know, all those kind of questions we're not able to address using this theory that we built.
Okay, thank you.
Okay. Good. So, conformal transformations. So let's start our treatment of conformal transformations. So, well, let's just make this note, which I said in words, but these cannot act as isometries. On R1 comma, let me write it in general, R1 comma D minus 1. So R1 comma 3 would be one example, but we're going to work just for a generality in D dimensions. And that's because those are already exhausted by Poincaré. Okay, we said that there can't be any more isometries. And so since the conformal group, as you will see, just adds generators to Poincaré, so Poincaré will be there as a subgroup of the conformal group. Minkowski space just can't take any more isometries. Well, it can't possibly act as isometries on Minkowski space. Okay, so that's just, again, the comment that I made before. But let's define now what is a conformal transformation. So a conformal transformation, let me call them CTs, okay? So a conformal transformation is, right now, it's simply a map that maps so x mu to a new coordinate. Let me call it x primed mu, okay, which is a function of the original coordinate x, leaving angles invariant. So actually one can have a great deal of fun in using like your favorite image and then applying a conformal transformation to it, and it makes it look very funny. I once was in a lecture where somebody used like an old 70s picture of Schwarzenegger posing in Los Angeles and then put like a conformal transformation on it, and it made him even bulkier. But I couldn't find that picture, but I will try to draw one, but without Arnold. But it leaves angles invariant. So what does that mean? Well, so for example, if you have like two curves that meet, then the angle, of course, here will be the angle between the two tangent vectors v and u. Okay, and so what you have is the angle between them, theta. Cosine of this angle is defined, of course, as the inner product divided by the length, right? Because the inner product can also be written as the product of the two lengths times the angle times cosine. And so now this conformal transformation now, well, it takes the line element, ds squared. So let's start with a conformal transformation just of flat space. So we take the line element dx mu, dx nu. Under this conformal transformation, what will happen? Well, it will become eta mu nu dx primed mu dx primed nu, okay, and this will leave angles invariant if this is just equal to omega squared of x, so some function of x times the original thing, dx mu dx nu. And why is that? Well, because if you take the inner product, of course, the inner product is just u mu v nu contracted with eta mu nu, okay? So if you use this form of the metric, then you have an omega squared at the top and an omega squared at the bottom. So the omega squared cancels out, so it leaves angles invariant. Okay, so under this conformal transformation, if you want cosine theta, just goes to cosine theta. So mathematically, conformal transformation is a map of this form such that the metric goes to some arbitrary function of the coordinates times the metric times the line element itself. Line element goes to an arbitrary function times the line element itself. And so what you can have is you can have something like, you know, you have your rectangular grid. For example, you start with a rectangular grid. Okay, so everywhere you have right angles and so on. Then you apply some conformal transformation. And what you can do is you can have like some very interesting bending of these things, but in such a way that the angles locally remain, well, in this case, right angles, okay? If I had intersections at other angles, then of course they would remain whatever these other angles are. But so you can distort it, you can change the volumes and all of that, but all the intersection angles are preserved. Okay, so now the question, of course, is what are these transformations? So we've characterized them in a sort of fairly abstract way. So let us characterize them fully. So we would like to now answer the question, what transformations are allowed? And basically, let's just go back to this line here, okay? So, okay, I can use the power of the iPad. I'll just put that here. Don't copy it again. I'm just going to use this to write a formula. So of course we can write this as eta mu nu, okay, and then the x primed mu. We can write then. Well, we can, if you want, we can divide this by dx alpha, okay, dx beta, dx alpha, dx beta, and we can rename these indices alpha beta if we want. Alpha beta, oops, alpha beta. And so now if we just equate the coefficients of dx alpha, dx beta in both of these, right? We have the equal sign. Then we find the equation eta mu nu, dx primed mu, dx alpha, dx primed nu, dx beta, that should be equal to omega squared of x eta alpha beta, right? So that's our defining equation of a conformal transformation, and that's the one that we will work with. Okay, clear to everybody? I think so. So what we have is we have a differential equation. It's a PDE constraining this map, constraining the map x mu to x primed mu. And let me say, let me make one more comment. I have sort of fairly quickly gone to just putting flat space here. So I'm now asking about the conformal, the conformal group of Minkowski space. I'm asking what are the conformal transformations allowed we can do to Minkowski space, but it's actually fairly easy. The manipulations are essentially the same to replace this by any metric that you want. So you could put here some other metric, and then you would be asking for the conformal transformations of a metric that is not Minkowski. And in fact, sometimes that is what people do. Like, for example, you could ask, just put a sphere there, for example, or whatever you want. So a couple of names to these things. So what x, the transformation x to x primed, it's not an isometry. Okay, this is not an isometry, but it is what people call a conformal isometry. So isometry, of course, means that the metric stays the same, but here the metric stays almost the same. It just changes by the factor omega squared. And this is what people call a conformal isometry. Okay, and the point is that if I put something other than the Minkowski metric here, then what I'm asking is what are the possible conformal isometries of this other metric. Here I'm asking what are the conformal isometries of Minkowski. Now, of course, every isometry, so if we do have a isometry, it is also a conformal isometry, is a conformal isometry, but one with omega squared is equal to 1, so a boring one. And then the last comment I make, which is often sent as a source of confusion. So this is actually something that really you should retain. It's confused me a lot over the years, but the point is that not all functions of omega squared of x can be reached by a conformal transformation. By a conformal transformation. So one might have thought that this function omega is completely arbitrary, but in fact, as we shall see, this partial differential equation also determines the possible omega squared of x that you can get here, the possible omega squared of x that you can get. Now, why is this often a source of confusion? So maybe this is the last comment that I will make before the break. It's often a source of confusion because in many applications, people also consider theories that have a Weil symmetry. And a Weil symmetry indeed is a symmetry under arbitrary rescalings of the metric of this form. Weil symmetry means this theory is symmetric no matter what omega you can put there. And so that symmetry allows you to undo any omega that's there. Conformal symmetry alone does not allow you to do that. Okay, so it's important to distinguish between Weil symmetry and conformal symmetry, and the conformal symmetry, as we will develop, only allows you some specific functions omega squared that can be there. Right, so I think I'll leave it here and I'll see you in 15 minutes, but please ask any questions if you have any at this point.
The boxed equation is an equation for Weil symmetry, not conformal symmetry.
It is the defining equation for a conformal transformation.
No, I get confused. Like, sorry, this last statement confused me.
Yes.
So you say for any arbitrary omega x, this box equation is the equation for Weil symmetry. But conformal symmetry is a subset of this. Sorry.
No. So let me just give you the direct mathematical answer to your last question. Conformal symmetry is a subgroup of diffeomorphisms times Weil. This is how it is related. But to be more concrete, the thing that is boxed here is the defining equation for a conformal transformation. But as you will see, we will analyze this equation. So we will look at what possible transformations can satisfy it. And this will both constrain x primed as a function of x, as well as the associated omega squared that one could possibly have. Now, okay, so this is just conformal symmetry. Now, maybe I shouldn't have made this Weil comment because it is a little bit subtle, but the point is that there are also theories which are Weil invariant, but Weil invariant is just a theory which is invariant under G mu nu goes to, let me just, to avoid confusion, let's just write e to the 2 sigma times G mu nu. So the theory, whatever the metric is, it is invariant if you exchange the metric by an arbitrary function e to the 2 sigma times the metric. That's if the thing is Weil symmetric.
Oh, I see.
And if that's the case, then anyway you can undo any function omega squared that you have here.
I see.
But because of the Weil symmetry.
I see. So, and you mean to say that there can be like symmetries which you cannot reach to the right sides by simply a coordinate transformation. I mean, if you can reach the right hand side by a coordinate transformation, those are conformal symmetries.
You let me just develop this in detail, and you will see what is. I think this is better. Yeah.
Yeah. Maybe
Okay.
I shouldn't have asked.
Yep. Yep. Was there another question?
Yes, I was gonna ask something, but then you said you'll develop it. What I was going to ask was, what is the group that corresponds to the Weil symmetry? Like, is it a compact or a simple group or something like that?
I don't think so. No, because it's a sub. No, I don't think it's a certainly not. No.
Okay. And
Okay.
even in 2 dimensions, these two are different, right? It's not like they become same in 2 dimensions.
Correct.
Okay. Thank you.
Okay, so I think I'll see you at 10:15 then.
Okay.
See ya. Okay, hi. So I think I'm just going to continue where we left off. So we're going to now develop our geometrical treatment, as it were, of the conformal transformations. Can everybody hear me?
Yes, we can.
Yes.
Okay, excellent. So right, so let's start by solving for linearized epsilons and therefore also linearized omegas, as you shall see. So let's solve for linearized conformal transformations. And so what we're going to do is we're going to say that x prime of mu is now the same as x mu plus some small generator epsilon mu of x. And let's say that omega of x is equal to 1 plus some small function which I call delta omega of x. Okay, and we work obviously in the linearized approximation. Okay, so let's just write it down. Let's write down this guy for a general metric g, because why not? So we have g mu nu x primed dx primed mu dx alpha dx primed nu dx beta that is supposed to be equal to omega squared of x g alpha beta. And what we're going to do is we're going to basically just linearize this now. So we get the equation g mu nu of x plus epsilon. Okay, I'm not writing the indices. And then I, of course, I have d alpha of x mu plus epsilon mu. Okay, and I have d beta of x nu plus epsilon nu. Okay, you understand the notation, of course, is d by dx alpha, d by dx beta. And that better be equal to 1 plus 2 delta omega times g alpha beta of x. So, right, so, well, you just expand it to first order in epsilon and you equate terms. And what you're left with is basically the equation that we all know, which is d mu epsilon nu, the symmetrized covariant derivative of epsilon. And if it were an isometry, this would be equal to 0, right? Because you would only have this term on the right-hand side. But of course, it's a conformal isometry, so it's not equal to 0. Turns out that it's actually equal to delta omega g mu nu. So that's the linearized equation for a conformal isometry. And I was able to do this for a general metric fairly easily. And the only thing that happened here was the covariant derivative appeared here and the arbitrary metric appeared here. But ultimately, let me just say, ultimately, we are going to be really only interested in the case where the metric G is actually eta mu nu. But in the meantime, we can write these formula for a general metric. It just makes it a little bit more, the treatment a little bit more general. And so that's right. So I just to say it one more time, I've already said it. This thing here is the equation that one would call the killing equation if there were 0 on the right-hand side, and this would determine all isometries of the metric. So all vectors whose linear, symmetrized derivative is equal to 0, those are the killing vectors, and all vectors whose symmetrized derivative is equal to this delta omega times g are the conformal killing vectors. But yes, maybe I should say that, by the way. So d mu epsilon nu, this notation is just d mu epsilon nu plus d nu epsilon mu. And I have put a factor of 1/2 there. Okay, so this is the symmetrized derivative, that notation. And obviously, if I used angle brackets, it would be the anti-symmetrized one. Okay, but I haven't put a box around this equation because actually what I'm going to do is I'm going to take a trace now. So now trace, so with g mu nu. Okay, so I trace this equation with g mu nu. And then what I get, of course, is I get trace of the unit matrix here on the right-hand side, g mu nu, g mu nu. So that gives me a factor of the dimension. And on the left-hand side, well, I'm going to get some kind of divergence. So this tells me that delta omega is equal to 1 over d times the divergence of epsilon. Okay. And so now I plug that back in here. Okay. And I get the actual equation that people would call the killing, conformal killing equation. So this is d mu epsilon nu symmetrized is equal to 1 over the number of dimensions, g mu nu times d epsilon. Okay. And it sort of immediately answers partly also Arinaba's question, because you see, once I know epsilon, I know omega because of this equation. So these two are linked. But what I've first succeeded in doing is I have an equation which gives me a condition only on epsilon. So now, obviously, this is some differential equation for the epsilons given the metric G, and I will now solve it. Okay, so just the name, it's the conformal killing equation. This is what people call the conformal killing equation. And the epsilon mu is a conformal killing vector. Conformal killing vector. People also like to call those CKV, conformal killing vectors. So we've written down those things for in general, but here we go again. So view single page. So now let's write them down. Let's write down, find the solutions of this equation for the case that G mu nu is equal to eta mu nu. So we're now going to find the conformal killing vectors of Minkowski space, and then also the isometry, the conformal isometry algebra satisfied by those vectors will be the conformal algebra. But for now, we just go and solve this equation in a straightforward manner. So we now have the equation, basically ordinary derivative on epsilon nu is equal to 1 over d times d lambda epsilon lambda eta mu nu. And we'd like to find all epsilon that satisfy this equation. So the technique is one takes further derivatives and further traces to finally get this into an equation, which is purely, we will see a very simple equation whose solution is immediate, and then you can integrate it back up to where we want to be by adding integration constants. So the first thing that we'll do, so these are just now, standard manipulations that one does. You look up the early treatments of the conformal isometries of flat space, and this is what you find. Or if you think about it long and hard enough, you will come to the same. So let's act with a further derivative, as I said. So let's call that derivative d sigma. And two more permutations of indices. You'll see in a second what I mean. Okay, so then what you can find is you can find an equation for d mu d sigma on epsilon nu. Okay, so I act here, okay, and I get an equation now obviously for the second derivative of epsilon. Okay, and the equation I get is this is equal to 1 over d times eta mu nu d sigma d dot epsilon, where I can maybe write this here. Okay, this covariant divergence I just also sometimes denote d dot epsilon. So it's it's d lambda epsilon lambda as I've written it there. Okay, plus eta sigma nu d mu d dot epsilon minus eta sigma mu d nu d dot epsilon. Okay, so what I was saying about the permutations is that you obviously get this term here by acting with d sigma on this, and then you add also the permutation of the indices mu, nu, and sigma. That gives you 3 equations of this type, and then you can solve these 3 equations to get precisely this combination of derivatives, d mu, d sigma, epsilon nu, and the right-hand side that you end up with is this. Okay, so that's maybe a small homework for you. It's not very difficult. As I said, you just take index permutations of this kind of equation by adding with another derivative, and you can find this equation here. Okay. Now, as I said, so we have added 1 derivative. That equation doesn't look particularly nice, but now if we add the operation of trace, now of course we trace with respect to eta mu nu. Okay, then I get an equation which takes the form of the flat D'Alembertian, so the D'Alembert operator in Minkowski space on epsilon nu. Now this is going to be equal to 1 over d minus d plus 2 d nu on the covariant divergence. And of course, we can simplify this a bit. This is 2 over d minus 1 times d nu d dot epsilon. That's really nice. But there's one more step that one can do. Now the final step, so maybe we can say 1, 2, 3. Okay, so now we apply d mu and symmetrize one more time. So one more derivative we add, d mu and symmetrize. Okay, so then what we get is we get the D'Alembert operator on D'Alembert operator on d mu epsilon nu, and this is going to be equal to 2 over d minus 1 d mu d nu on d dot epsilon, which we can rewrite as 1 over d eta mu nu box of d dot epsilon, using actually the conformal killing equation that we have up there. Okay, and so our final answer, the final equation, this is the one that really we analyze, is d minus 1 times the box acting on d dot epsilon now is equal to 0. Okay, so this now is an equation which is extremely simple, and well, let's give it a name. This is the equation dagger. And so that equation we can solve immediately, but maybe first, okay, let me actually can transfer this onto the other page. Okay, this is the equation, copy. Okay, paste. Okay, so this guy, first let me make some comments. Okay, so we have some special cases, obviously. So we have the case that for d is equal to 1, every function epsilon mu of tau is a, or I guess epsilon of tau is a conformal transformation. Okay. Those of you who have seen treatments of conformal group in one dimension, they already are familiar with this, that any reparametrization in this dimension is a conformal transformation. We should, of course, specify, just to be explicit, right? So we were talking now about conformal isometries of R1, comma, D minus 1. So D is space-time dimension. I'm just reminding you, okay? Space-time dimension. So D is equal to 1 is really a 0 plus 1 dimensional conformal transformation, okay? So that's already a special case. Also, D is equal to 2 will be special. That is not so evident from this equation, but we will see that later, okay? And now for now, okay, so those comments. So now for D greater than 2, this is what we're going to focus on for now. As I said, we will make some more comments on the low dimensional cases. But for D greater than 2, well, this equation immediately gives us, so this just tells us that the D'Alembert operator annihilates the divergence of epsilon. So that means that the divergence of epsilon, okay, has to take the form A plus B mu x mu, right? Roughly speaking, as you probably have already realized, of course, this means that the second derivative, okay, of this thing is 0 with respect to space-time. And so it can be at most linear in space-time, in the space-time variable x. So it can have a constant A, plus then a term that is linear in x mu. And the most general term that is linear, we can write by some arbitrary parameter b mu contracted into x mu. So that's the immediate obvious solution of this equation, right? So that's one of the advantages in having gone through these manipulations where we increase the orders of derivatives and we juggled around a bit with index permutations and taking traces, but more or less we just increase the number of derivatives to end up with this extremely simple equation, okay? So then what we can write is, so let me see how to say best. Well, so d mu, d sigma of epsilon u should be some constant, right? So we write d mu, d sigma of epsilon mu. This should be a constant, but because it carries indices, let's call it c mu sigma nu, okay? So this is some constants or some constant, okay? And then what we can write is, in order to satisfy this equation dagger, okay, we take the solution ansatz that epsilon mu is equal to a mu plus b mu nu x nu plus c mu nu sigma x nu x sigma. So what's going on? This is much simpler maybe than what I'm writing here suggests. So you see, this just means again that if I act with 3 derivatives on epsilon, I need to get 0. So epsilon better be the most general expression I can write down up to quadratic order in x mu. And the most general thing I can write down that has 1 index, okay, is going to be a mu plus, now I have to leave 1 index over, so I call that b mu nu x nu. That's the linear term in x. And then there's a term that's quadratic in the x's, and I call that c mu nu sigma x nu x sigma, where c mu nu is obviously defined by the fact that if I take 2 derivatives, I get these constants. Okay, so this is, if you want, our most general solution ansatz.
Sorry?
Yes?
But because we have gradients, shouldn't it be, there could be other solutions, right? Like wave solutions? For the D'Alembert equation, you don't need to have something that is linear, or am I wrong?
Sorry, you're saying that, let me see, so you want to write, let me think, so you have, sorry, so you're saying in this equation?
Yes, this one.
You want to write that the divergence of epsilon, let me see. I mean, this is essentially what happens in 2 dimensions. I'm blanking right now why it doesn't happen in higher dimensions. Well, maybe let's go on with the analysis and we'll understand why it doesn't happen in higher dimensions. But in 2 dimensions, what you say is essentially correct. Okay, let me go on and we'll probably understand why. Okay.
Yeah. Yes.
So but the point is that what we do is we go up in the hierarchy of these equations now. So what we do is we plug this ansatz now into the conformal killing equation and determine each term, okay? So we plug into the conformal killing equation and determine each term. As by term I mean things like A mu, B mu nu, and C mu sigma nu. Okay, so we plug this into the original conformal killing equation. And so then what we find is, well, we can do this order by order in x. So we have order x to the power 0. Well, then actually any epsilon mu of the form A mu solves the conformal killing equation. So there is no further constraint on the parameter and the parameter A mu. Order of x to the power 1, so x mu. Okay, this gives us the equation. Well, we plug in epsilon mu is equal to b mu nu x nu. And the conformal killing equation then tells us that B symmetrized should be equal to 1 over d times B lambda lambda eta mu nu. Okay, so that means that B mu nu has some antisymmetric part plus alpha times eta mu nu, where basically omega mu nu is an arbitrary antisymmetric matrix, which is basically going to be our Lorentz generators, and alpha is a parameter. So the symmetric part is proportional to the Minkowski metric eta mu nu with a parameter alpha here. So omega mu nu is equal to minus omega nu mu. Okay. And so, well, we can say that at this order, epsilon mu is equal to omega mu nu x nu plus alpha times x mu. Okay, and the point being that this we recognize, this is going to be just a Lorentz transformation. This is really the omega of the Lorentz transformation. And this thing here, okay, that's ugly. That thing here is a scale transformation. Okay, where we just rescale the length of alpha of x. And so now the last one is order of x squared. What we have here is we have epsilon mu is equal to c mu nu sigma x nu x sigma. And the conformal killing equation basically gives us a constraint, which one can boil down to epsilon mu is equal to 2b dot x, so the b with one index, into x mu minus b mu x squared. And this thing here is what one calls a special conformal transformation. We will illustrate this in a second. Conformal transformation. So what you want, if you want, what we have is we have found here basically the translations. Okay, we have found here Lorentz, but in addition to that, we also found a scale transformation and one further transformation, which people like to call the special conformal transformation. So let me summarize. Well, we've uncovered x mu going to x prime mu of the following form. Of the form, well, we have the x mu plus a mu, which is of course translation. We have lambda mu nu x nu, which is Lorentz. So I'm writing, by the way, already the finite forms of these transformations. We have written down the infinitesimal ones here. We have something like lambda times x mu, which is nu, which is a scale transformation. people also like to call this a dilatation. And then finally, we have the much less obvious finite form of the special conformal transformation, which is x mu minus b mu x squared divided by 1 minus 2b dot x plus b squared x squared, which is, well, as I said, what people call a special conformal transformation. Okay, and the infinitesimal form is again given here, and the infinitesimal form of the scale transformation is given here. Okay, and so let me just say, conformal transformations is therefore basically Poincaré, but then union two more things, namely the dilatation and special conformal. And finally, the way that we've constructed them, but I've emphasized it a lot, is that these are not the isometries of Minkowski space, but they are the conformal isometries of Minkowski space. So they don't act as isometries. There is only a subset of them which act as isometries, and those are these Poincaré ones. And as I said, every isometry is a conformal isometry, but with omega is equal to 1. And so what we, of course, conclude from that statement, and we could also calculate it, that this one has omega is equal to 1. We know that already, but these ones have omega not is equal to 1, and we could work out what their omega is simply by going back to this other equation. So now, presumably, there is a simple answer now to Sergio's question from before, and that's that if you did like have a general wave solution of this, right? If you went up the hierarchy, that the wave itself does not satisfy the original equation, namely the conformal killing equation itself. Okay, these are the only ones which also satisfy the conformal killing equation. Okay?
Yeah. Thank you.
And by the way, this also tells you why it works in 2 dimensions, because in 2 dimensions, the D'Alembert operator does actually factorize into left and right moving. So dt minus dx and dx minus dt. And because of this simple factorization in 2 dimensions, those kind of solutions actually also satisfy the conformal killing equation. Higher dimensions, they do not. Okay.
I have another question, Julian.
Yes. Let me just arrange this a little bit more and make one more comment, and then you can ask your question. So I said this already, but I want to just emphasize it one more time. The fact that I wrote down here the finite transformations is because I know the finite transformations. And for most of these things here, I think maybe late, oh my God, a bird literally just crashed into the window, and this was not good for the poor bird. Oh, okay, sorry. Right. So getting the finite transformations is okay for most of these. But to get the finite from the special conformal transformation is actually quite difficult. I believe there is actually a question on that on the examples sheet. Okay, Adrian, your question.
Yeah, so I was going to ask, because in the definition of conformal transformations, when we introduce the transformation of the line element,
yeah,
we said that by definition, the conformal transformation is such that you pick a prefactor that is omega squared. So this is positive always.
Yes.
So where was the fact that this is positive, where was this important in the analysis that we just made? Because indeed we have
no, it's a good question. I don't know if it's anywhere. I need to think about this a little bit, but what happens is that if you calculate the omegas for our friends that we have here, it is automatically positive. But I don't know if we've used anywhere that constraint. maybe we probably had to.
Mhm.
Yeah.
Okay.
Okay, so let me see what I'm going to do now. So I have about 15 minutes left. Yeah, okay, let me give you just some intuition about this special conformal transformation. Okay, so this can be seen basically as a combination of inversions and translations and then inversions again. So let me show that. So if you do an inversion, so x mu, okay, under an inversion I goes to x mu over x squared. Now this inverted version of x mu, okay, this I can now translate. So I'm going to let this go to x mu over x squared, and I'm going to translate it with hindsight by a particular vector, namely minus b mu. And now I invert this guy again. Okay, so I do the same transformation that I did on x mu. So I divided it by its length squared, okay, to this guy, the translated version of the inverted vector. And I get x mu over x squared minus b mu over x mu divided by x squared minus b mu all squared. And if you multiply that out, what you get is you get x mu minus x squared b mu divided by 1 minus 2 b dot x plus b squared x squared, which is exactly the special conformal transformation. Now, why have I done that? So because what you will see actually for the rest of our treatment of the conformal group, the generator that corresponds to the special conformal transformation essentially is like a second momentum generator. It behaves to all intents and purposes as if it were a second momentum operator. And the reason is that it is kind of a momentum operator. It's just a momentum operator that, with poetic license, basically acts at the end of the world, you see. So if you go to x mu, you invert it. So if you're at the origin, you go to the end of the world, you go to infinity. So you don't translate with respect to the origin, but you translate with respect to the point at infinity. Okay, but it is just a translation there. So you basically, put everything upside down. So the origin becomes infinity. Then you do a translation, and then you put everything again downside up if you want. And the result of this is a special conformal transformation, which is part of the conformal group of symmetries. Okay, I've described this once before when I described the conformal symmetry and people got confused. The point is that it is not necessary that inversion is a symmetry, right? The only thing, because it is not part of the conformal group, the only thing that's important is that if I do this chain of operations, that's the same as doing a special conformal transformation. We know that a special conformal transformation is a symmetry. All that this sequence here gives you is some kind of intuition why the special conformal generator also transforms a bit like a momentum, okay? Because it is like an inverted, yeah, as I described it, it's a transformation. It's just a translation, but after you've done an inversion. Okay, so then the other thing is that in 2 dimensions, so this is the intuition about SCT, then in 2 dimensions, so that means D is equal to 2 here, okay? So what we can write is actually, we can write ds squared is equal to dx squared plus dy squared is equal to dz dz bar, where I've defined z to be equal to x plus iy, and then z bar is equal to x minus iy. Okay, and you can convince yourself that here any holomorphic function, so any z going to f of z, and so z bar going to f bar of z bar, is a conformal transformation. Okay, and this is this left mover, right mover story that I've just been saying, but you can just convince yourself that in 2 dimensions, any holomorphic reparametrization of this coordinate z and any anti-holomorphic reparametrization of this coordinate z bar satisfies the conformal killing equation. And so this means that in 2D, the conformal group is a group of full functions, so is infinite, and therefore is much bigger, if you want, much bigger and much more powerful than for d strictly greater than 2. And actually this leads to the topic of Virasoro symmetry. Virasoro. So the representation theory of the conformal group that we go through will be the one that is applicable for d strictly greater than 2. Okay. It is also applicable for d is equal to 2, except that in 2 dimensions there is more. So there is what we will develop and much more, and the structure which encapsulates all of this, so what is called the conformal group in the strict sense, plus what you have in 2 dimensions, this is called the Virasoro group. Okay, so just as a, maybe also just as a name, so one often speaks of, so the d greater to 2 case is often also referred to as the case of global conformal group, as opposed to what you have in 2 dimensions, which is associated with the name Virasoro. But of course, the global conformal group in 2 dimensions is a substructure within this Virasoro group. Okay. And well, maybe the last remark that I make here is, for this reason, because the conformal group in 2 dimensions is so special, I saw there's a question, we can say it in a second. 2D CFT is a big subject in its own right. It's mathematically extremely beautiful structure, and conformal symmetry in 2 dimensions in some sense is much more powerful than it is in higher dimensions. And so what you can do is you can derive many non-trivial results that are not accessible in higher dimensions, because the conformal group is just that much more powerful in 2 dimensions. That was a question.
Yeah, Julian, sorry.
Yes, of course.
I wanted to ask you if this is, there is a similar feature, I mean, this kind of, as you were saying, left-right, left-right application of the conformal symmetry in any even, no, sorry, not even, when you have an equal number of space and times dimension case, or not? Because I mean, you need only to factorize the Lambertian, no, to have this.
What you're saying is that if you take, for example, a 6-dimensional space with 3 time directions.
Yeah, or R22. Yeah, or yeah, yes.
To be honest, I haven't thought about this, but my spontaneous answer would be no. That's not the case. And in particular, the conformal group of, say, R2, 2 is just a real section of the complexified version of the conformal group of R1, 3. And it's in particular, there's no such thing as a 2D conformal structure hiding there. But what I can say is that there is a similar structure related to this so-called super translation group. So if you look at if you look at the group of super translations, so the BMS group that acts on the celestial sphere in Minkowski space, then in fact that has some kind of infinite dimensional structure in any dimension. So maybe this is the group that you're looking for. So you want to look at this BMS type group, the Bondi Metzner Sachs group or something like this. Okay.
Okay, thank you.